haven't asked many questions during the workshop, but I really have enjoyed all presentations. And so my talk will be very similar in parts to Decio's talk and also some points from Otavio's talk. And so you are going to see a lot of things that you had already seen before during the workshop, but I hope arranged in a different way. So I will be talking about anomalies from empirical sciences. Can I ask you, Otavio, to let me know when I have spoken for 20 minutes? Yes.
How long do you have?
Half an hour, and then 10 minutes for Q&A. So, thank you. So I have been working on inconsistencies in science for a while, and something that I discovered is that as many logicians would start researching in this field, they would assume that certain anomalies resemble inconsistencies or contradictions. And then they go from that point to say what an anomaly is when it looks like a contradiction, and how do we deal with it, and so on and so forth. So that was my initial point of view when I started working on this. But the more cases I research, the more discovered that this is not so clear for other philosophers or historians of science, or also other logicians. So what I will try to relate today is different types of defects that shape the anomalies. So not only contradictions, not only gaps, but a variety of those. So that's it. I will try to cover these 3 points, but very weirdly, you only will see them by the end of the presentation. So I will try to emphasize the holistic nature of epistemic bodies in science and how they relate to certain types of anomalies. I will emphasize also this interconnectedness in between defects, so contradictions, vagueness, imprecisions, incompleteness, gaps in general, etc. And then I will also say that there is a sort of transition between contradictions and gaps and other types of defects. So that said, if you have any questions at any moment, please feel free to interrupt me. The plan is going to be 4 parts. First, yes? You have questions already? No? Okay. So I will go through some preliminaries, then I'm going to talk a bit about holism, and then I will say more about defective information and some final remarks. Now, this is a talk that helped me to revisit a paper that I wrote many years ago when I started getting familiarized with inconsistency in science. So my view then was that holism is almost everywhere in science. Our theories are from different perspectives, very holistically integrated, and also the models of those theories and the observations that we have for testing those theories are in a holistic manner put together. So that was my initial view, and it was very much challenged by the idea of having contradictions, because if we have holism surrounding all epistemic bodies in science, then it's very hard for us to be able to point out real contradictions and explaining how to stop them, how to deal with them, and so on and so forth. So that has evolved in a sense, but I will say more about it. So where to start? From the idea of what an anomaly is. So anomalies consist of the presence of a statement, generally some kind of observational outcome. This is an issue that has already been raised during today's sessions. And that is a general idea of what an anomaly is, especially when we are talking about empirical sciences. As Otavio mentioned, there are certain problems from a perspective of Laudans, for instance, that are conceptual, and then there are problems that are empirical. And we can say, those problems are also anomalies, and then we have anomalies that are conceptual and anomalies that are empirical. But I will assume that the most interesting anomalies in the empirical sciences are those that relate to observation. So that's the first point. I tend to look at Lakatos as one of the first people, and to me, my preferred people to describe what an anomaly is in empirical sciences, because his only concern was how a theory relates to a particular statement and whether that statement validates or reinforces or gives some approval for the theory. And his worry was, well, if you have something that is anomalous, then it will, in a sense, be a defeater for the theory, or will be a problem for the theory. This is also something that has already been very much stressed during this the talks of today. But then we have in the literature, from Laudan's perspective, for instance, the distinction between having gaps, or what Theo Kuipers is going to call later on lacune, and which are holes, either explanatory or predictive, or observational gaps. And then you have logical contradictions. These two things are very different because the way in which we react to those is very different than anomalies. And I think this was said by Carol. Anomalies are only important from our humans' perspective, from agents' perspective. So the way in which we interact with anomalies is very revealing about their nature. So when we find a gap, we usually are okay with it in science. We assume that there is a type of constructivism that underlies any type of science. And so if we don't have all the information at a certain point, that's okay. Because in the end, in the long run, we are going to fill all these gaps. So that's not a problem. But when we find a contradiction, that really tells us something about how bad we are doing science. And so that is the reason why people are more skeptical about accepting logical contradictions than tolerating gaps. So this is an important aspect. I'm going to assume that anomalies, again, are more related to observation. And in order to address this, we have to commit to the fact that there is a way for us to distinguish between theory and observation. And so, and that in order to find an anomaly that looks like a contradiction, for instance, that we are finding an observation that can sensibly be interpreted as a negation of a prediction. Because we never find a negation, right? That in the empirical world, if I say this marker is going to be here tomorrow, and this is a prediction, and then it's not exactly here, but it's around the area, then it's not clearly a negation. And one can say, this prediction was A, and this observation is B. But the fact that they are different is not enough for saying that they are mutually inconsistent. Sorry, I've been dying of allergy these days. My voice is not at its best. And so we have to be able to assess this. For the case of the perihelion of Mercury, for instance, the problem was so strong, the prediction didn't match the observation in such a way that it was actually something that people were reconstructing as a contradiction. So, as I said, we have an anomaly, and then intuitively we have two cases. Either we lack information, we have a gap, or there is a mic that is open, so maybe it would be a good idea to close it. Thank you. And then you have a contradiction. In the case in which we have a gap, we usually explain it by saying we are ignorant. It doesn't really matter, right? So in the long run, we are going to get enough evidence, and that will be it. And ignorance is part of science and scientific development, so it's okay. In the case of the contradiction, as I said, our intuition is we are doing something wrong. But what I have discovered is that the large majority of explanations that we find in science, and especially in philosophy of science, even made by the paraconsistent logicians about the cases that I have studied, is that contradictions are the result of ignoring something. And what is the thing that they think that we are ignoring? Keep in mind that it's empirical sciences. What do you think is what we can ignore? in order for a contradiction to appear. So, what do you think?
It's a long story. So.
Usually, what philosophers have reconstructed is that people tend to ignore the truth value of these two things that seem mutually inconsistent. So they are not encouraged enough to reject any of those. And that is the reason why they have to keep them. Meanwhile, they get more information. So in the end, what is happening behind contradictions is a type of ignorance. I tend to call it ignorance of theoretical structure, or in this particular case, it's factual ignorance. You don't know which one of the contrary elements are, the mutually inconsistent elements is false or is true. And so the problem is what happens behind this factual ignorance, what is causing it, and particularly what causes the resilient character of anomalies. Because gaps usually tend to be solved if they are not that challenges. Then you get another experiment, you get more evidence, and then you fill the gap, and that's it. But in the case of contradictions, they are very interesting because they can last for a long time. So the example that Ottavio was talking about, it lasted problematically over a century, and people were thinking about this. Even when Newton and Leibniz were discussing, they were talking about the contradictions that were behind the calculus, and still couldn't solve the problem. Newtonian dynamics and the problem of the perihelion of Mercury lasted a century as well. So the problem with contradictions is that they are very resilient. So what causes that resiliency? And what I tend to argue here is that we are lacking information in both cases. When anomalies are resilient, we lack information about how to arrange epistemic bodies. So the reason why we cannot infer, in a sense, the truth value of two elements of a contradiction is that we lack of understanding of how we can infer in that particular case. And then that's something like ignorance of a structure. And I like to call it of theoretical structure because we are talking about scientific theories or scientific models. So it's very much theory laden. And then here is where we are back to Decio's intuition, because we have some options, as Decio was mentioning yesterday. So we can reject the anomaly. We can say, this is very problematic. But in the case especially of contradictions, that means that we have to reject both parts, not only the one that we don't like. We can find motivation for tolerating the anomaly, or we can accept it. So which one do you think is the most rational way to go? Ignore it. But it's not part of the three options. So what happens is that this is very important. It happens in empirical sciences. We often, when we find an anomaly of this case, we cannot reject it. The reason, as Ottavio was saying, is that often we don't have an alternative theory to substitute the one that is raising these problems. So how are we going to reject it and leave it empty-handed? Can we accept it? So, sorry, here's rejection, here's acceptance, and this is motivation for toleration. So for the case of acceptance, it's very, very weird to think that we can accept, for instance, a contradiction, or that we can commit to the fact that reality is gappy, that's okay, that there is a truth behind that. So especially if we look at the history of science, we don't have any evidence of that. So it's very rare to say that, hey guys, there is some echo there. Can you close the mic that it's on? I'm going to close it myself. This one. Yes, thank you. So can we accept it? No, we cannot, because we don't have any evidence, historical evidence, that can motivate us to say, let's become dialeteists, let's say that contradictions are true, or let's really take seriously the option that reality is gapy. So we are, in a sense, only with the option of being motivated to tolerate the anomaly. But that doesn't mean that we are able to do it. So this is something that I really enjoy from a paper by Ottavio. Yes? So, no, maybe this move a bit, but then I don't know how to. No, it's here, but this wasn't the best option, so no. And here, if you don't have any, yeah. It's better. Okay. So Ottavio has a paper in a collection of 2017 that it's a very interesting collection if you are involved in these topics, that sheds light on which are the options that we have. And this also coincides with Decio's intuition, because Decio was saying, let's consider the option of cutting the theory, right? And saying these two parts do not merge. And also we have information restrictions. So that means that some parts can merge under certain circumstances. And then we have precautionary strategies. And Ottavio has a very interesting interpretation of many of those, because he says you can have this fragmentation and preserve your classical intuitions, or you can have fragmentation and preserve paraconsistent intuitions, and like that for the other two. So once we find which of these type of mechanisms can actually help us to navigate the logical space that emerges from the theory and the observation, we can, in a sense, find a way to accommodate and to tolerate rationally the anomaly that we are dealing with. So in that sense, we can overcome, at least partially, the ignorance that helped us to find this anomaly at the beginning. And it doesn't mean that we solve the problem. We don't have a solution for the anomaly. We didn't solve the contradiction necessarily. We didn't fill the gap. But what we have is a rational way to explain how we are working with this information. Some of the strategies might look like Ottavio was mentioning in the case of Newton's. Newton had an explanation of what infinitesimals were doing and why we shouldn't take them seriously. And Leibniz had also an explanation, and they weren't equivalent, but they helped them to explain why their practice was rational, even though they acknowledged that they had an anomaly over there. So now the question is, how do we select these inference patterns? And this has to be done case by case, but it is very important to find out which are the elements that are, in a sense, being involved behind the anomaly, so that can shed some light on which are the strategies that we can adopt. If we look at the options, and if we distinguish between theory and observation, and we assume that we have a little bit of background on classical logic, it's very easy to find, non-classical logics, it's very easy to find some examples of this. So fragmentation, there is a paper 2014 by Kevin Davey, and then there was a book from 2013 by Peter Vickers, in which they tried to explain what happens informally in these cases. So in the cases, for instance, of the early calculus, Peter Vickers says what happens is that you have two proofs. And so these two proofs don't merge necessarily. You can take the result from the first proof and then you put it in the second one, but you don't have the fact that infinitesimals are 0 and distinct from 0 at the same time. So there is a sort of fragmentation and also an information restriction thing. Then you have Chonga permeate, for instance, by Brown and Priest, that was applied to this particular case, and that said that, but with a paraconsistent background. So you can merge parts of the chunks that you have made with the theory, and that will give you a sense of tolerating the contradiction in a rational way, keeping your good results, avoiding logical triviality. And then you have precautionary strategies, and there, Decio mentioned this, there is an infinite amount of adaptive logics. And adaptive logics, what they tell you is reason as if the logic, that underlying logic is classical, unless you find a contradiction. Then when you find a contradiction, you just mark it. Change a bit your reasoning, start considering that the contradiction is problematic, where is it coming from, and so on. And try to trace the inferences that allow you to derive this contradiction, and then cancel some. So it's more about if everything is safe, try to preserve consistency as much as possible, try to be safe, and so on. But the first issue that we have with all these three options is that they assume that we can actually effectively identify and cut parts of our theories and models. And I start this talk by saying that I don't think that's the case, and I am not alone. So Duhem said this very early behind, and his concern was people tend to believe that when there is a problem, the physicists can identify the root of that problem. And that's insane. People cannot do that. Because think about the anomaly of the perihelion of Mercury. What happens there is that you can identify the contradiction. This is the prediction that the theory entails about where Mercury should be, plus the observational report. But that doesn't solve, if you isolate that part, that doesn't solve the problem, because the contradiction is coming from the combination of information that is within the theory and Kepler's laws and the information that you have about Mercury, and the fact that it is inaccurate to describe the actual phenomenon. So it is very hard to isolate the parts that are doing wrong, in a sense. I don't know what happened here. So, and actually, the problem goes beyond that. So it's not about the theory and maybe an observation, but the problem is that theoretical description of a system rarely takes place in isolation. So our scientific bodies are the combination of a lot of things. We are doing physics, but we are assuming knowledge from chemistry, and we are assuming certain type of mathematics. And if we are doing biology, we are assuming all the other ones, and so on and so forth. So all our scientific bodies are very much entrenched. So, okay, holism is part of science. Duhem, Quine, and so on have already convinced us of that. But the question is holism relevant for analyzing and explaining anomalies, especially from us, from our corner, the philosophy corner? Now I'm going to go through an example. Do you have any questions so far? How? Okay, let's go to that example. So who knows what a neutrino is? Neutrino is a tiny particle which was discovered in the 30s, almost one century ago, by Pauli. And so at the beginning, it was just a subatomic particle that they decided that was very useful to calculate beta decay phenomena. And so they assumed the properties of neutrinos, taking into account how successful it was solving the issue. So it was just a theoretical entity, and at that moment they didn't know whether neutrinos actually exist. So they bring out these properties. They say subatomic particle, a fermion, electrically neutral, ideally with a tiny mass, but preferably no mass at all, and interacts only with the weak interaction and gravity. And so we have a lot of neutrinos coming, but they almost don't interact with us. So you have to have a ton of neutrinos going through your body, and only one will interact with your body. And so the epistemic backup was that if neutrino existed, then they could explain beta decay. And it was a theoretical entity for a while, but physicists thought that it was worth pursuing to find out whether it existed or not. So the idea is they don't emit nor absorb light. This is very problematic for designing an experiment. They don't have an electric charge. They are extremely lightweight. And the only way to study them is by their interaction with the weak nuclear force. When a neutrino interacts with an atom, it produces another particle that can be detected and measured by us. The sources can be natural, so sun, cosmic radiation, etc., or man-made. And to consider this one is very problematic because then we have to think about the sun, and it's very far away from us, and it's the 30s, so man-made. Particle accelerators, nuclear power plants, and only in these cases we can have a huge number of neutrinos or antineutrinos or a huge detector. And the urge that physicists had at that moment was that large that they decided to create the project Poltergeist. So this project consisted on creating a mini nuclear bomb and throwing it somewhere in order to find out whether neutrinos can be measured or not. That has to tell you how much physicists were engaged with the idea of testing the existence of neutrinos. So the project didn't survive that much, but it tells you the interest that was growing in the community. So at the 40s, late 40s, the discussion was already, in a sense, very robust, and they thought that they could test the existence of neutrinos. And in the 60s, somebody contacted Bacall, and he designed something that is called the standard solar model, which is a model, a mathematical model that allows us to infer certain properties of stars, including our sun. And then Ray Davies, almost the same moment, was contacted by Bacall and said, can we design an experiment? Can you design an experiment? He was a chemist originally, and then they designed an experiment, went to a conference. He got 10 people in the audience, talked for half an hour, nobody asked any questions. And that, in a sense, said that everything was very intuitive for the chemists, radiochemists. And so they were thinking that this is nonsense, like it's okay, why is this man talking about us in an important conference and so on. And so he designed the experiment. Bacall works a bit more in the standard solar model, gets the prediction, and then send it to Davis. He runs the experiment. And the problem is that in the end, we had, say, 1/3 in the observation from what was initially predicted. And this was a huge problem because the mathematics behind this was very solid, very strong. Everybody trusted. Again, the experiment by Davis, everybody was like, this makes a lot of sense, so it shouldn't be mistaken. So they go to their places for a year, they rework everything, and then they go back to the problem. And while closer, the predictions were still not meeting the observation. So say that this, in a sense, represents the experiment. And the idea was that they were relating argon-37 with chlorine-37 for the first time to see whether they could create neutrinos in the long run. So the first one to blame was this combination. Then it was one of the first underground experiments that they developed. It was a super huge full charcoal trap. And then they said, maybe something here in the design of this part, like the pure instrument, the pure location is mistaken. Then there was a Geiger counter that was supposed to give a click for every presence of neutrino that they had. And then they said, maybe the counter was not working well. And then they had, this is one of the first experiments that involved data analysis. And so they had to design the data analysis tools to filter these clicks, to get rid of the noise. And then they had an observational lab. So everybody was blaming every single step. what happened, including that neutrinos did not exist, and so they were not observable. So it was making a lot of sense that the experiment didn't go well because they didn't exist. What happened is they changed the combination of the elements that they were mixing. It made it closer, but it wasn't enough. They checked again the location, they changed the data analysis, and part of the problem was here. Because later on, they discovered that neutrinos are particles that change the type of neutrino. So they change flavors depending on how they are traveling. So at some points, they were measuring one type, the ones related to the electrons, but there are 3 types. So when they were looking for one, they were missing the other 2. So the prediction was quite good, but the problem was that the theoretical body wasn't as good as the prediction. So conceptually, we weren't understanding neutrinos. That said, in this case, what happens is that there is a holistic arrangement between the assumptions of what neutrinos are. And this assumption is underlying the experiment, underlying the theory, underlying our intuition of what is the observation that we are reporting, and so on and so forth. So in this case, the problem wasn't easily to solve. It took many decades. The problem arose at the end of the 60s and ended up being solved in a sense, explained only in this century. But even though there was a Nobel Prize associated to it when they discovered that they had a tiny mass, and that explained how they could change the flavors, now there is another anomaly about how the hell they get the tiny mass. And one hypothesis is that something like sterile neutrinos exist, but in general, neutrinos behave very anomalous. And the problem is that every single theory that we have to explain them, and every single model that we're using, even conceptually, is underlying, it's underlined, but a lot of ignorance and a lot of lack of understanding of what neutrinos are. And it's still a very problematic particle. So in general, some lessons that we can take from this is that there is a group of things that are called defective information that includes gaps, contradictions, false information, partiality, incompleteness, among others. And the combination of all this information, of this type of the issue in which we can not necessarily identify or explain what type of anomaly we are dealing with. If we go back to the anomaly in the perihelion of Mercury, there is people saying, oh, this is a clear gap, and there is people saying this is a clear contradiction with exactly the same information. The only way in which they are characterizing the anomaly is terminologically. So what is the problem? We are lacking explanations that we got only in relativity theory, or we are having a contradiction between theory and observation, and the theory is inconsistent and will remain being inconsistent with the observation because the problem cannot be addressed from the theory in itself. You have the same problem in Newtonian early calculus. People like Peter Vickers would say that what happened is that you have a lot of idealizations there, false information being useful, but there is no contradiction. And you have other people saying that there is a legitimate contradiction over there. So we have to be aware of that the same anomaly can be associated different defects depending on our background. And now, it is important to say that these defects relate in an important way, because when people say that there is a gap in Newtonian physics that give rise to the problem of the perihelion of Mercury, they have something accurate, but also when people say something about contradictions. So, and what we can see in the case of Mercury is that at the beginning, physicists were taking it as if it was a gap. First, it was an error, then maybe it is an observational gap. We cannot see the other planet that is in between Mercury and the Sun, and that is causing this problem, and so on. And only later on, the problem became actually a contradiction when it was so resilient that couldn't be solved. And then people, in a sense, quit the enterprise of fixing it in a consistent way. So In the case of Bohr's theory of the atom, there is people that say that initially they move from the intuition that this was a contradiction to a case of incompleteness. Ottavio has a paper in which he deals with this example from the 1970s. And no, from 1997. And in the case of the solar neutrinos problem, what happens is that they move from a problem that initially was thought to be about incompleteness, that if you see the interactions between the scientists, they were calling it a contradiction, and then they moved to something that it's more vagueness or ambiguity about what neutrinos really are. And this is case-by-case analysis, but it sheds light on how there is an interconnectedness of these defects. And Ottavio and I, we are editing, and we have been editing for 4 years already. We should commit online to send it to the world, a book on defects and science. Decio has a paper over there, and we have a lot of these discussions around anomalies. Maybe nobody calls them anomalies in the books, but the use of different types of defects in science and how scientists are okay or are using different techniques to deal with them. That's it. I hope we have covered the holistic nature of scientific theories, especially in the case that I was talking about, the interconnected defective information, and how sometimes we cannot distinguish very adequately behind an anomaly, whether it's a contradiction, a gap, or a case of something else. But that it's very important to understand that maybe if somebody is saying that it's a gap and somebody else is saying that it's a contradiction, it is because it had both shapes in different moments in history of science. And then that obviously from that there is a type of transition between gaps, contradictions, and vice versa. And that's it. Thank you very much.